All right, do you remember how to do that one? There's the answer. Find the magnitude of an angle. No, magnitude of a vector. Remember how to find that? Those double bars mean magnitude. Did you guys finish up 4.2 okay? What was 4.2? Oh, law of cosines, huh? Law of cosines. So finish up law of cosines. So we're on to vectors. So we're not far from another exam, actually. I don't know when that's going to be. I'm looking at the schedule. We were scheduled to have a practice exam today, but we're getting behind a couple days. So probably, next week will be test week. Monday will be the practice exam. Wednesday will be the real exam. So next week, plan for next week. So, all right, anyway, how do you find the magnitude? Those double bars around a vector, they mean magnitude, which means length. Like, how long is that vector? How long is that vector? If I was to draw this vector, I could do that, right? Let's draw it. You don't have to. It's not required, but I think might be good just to see it. So, if you were to draw that vector on the axis system, where would it sit? What does minus 7i mean? Yeah, that means like right, left, right? The I is right, left, the J is up, down, huh? The I is like X, and the J is like Y, basically, right? It's like giving me the coordinate minus 7, 15, basically same thing, huh? Right, so you just go back 7, 1, 2, 3, 4, 5, 6, 7, and up 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So right about there. So there's vector V, which is minus 7i plus 15j. Minus 7i plus 15j. Back 7 up 15, right? So there's the vector V. And what they're asking me is, how long is that vector? That's what magnitude means. How long is that thing?
Does the vector always come off of the origin?
No, remember, you can move them around. Good question. Yeah, I just think it's easy to draw them that way, but good question. You could really move a vector anywhere, right? Remember, they're not anchored. They're a loose boat. They're just floating. They got no anchor down. So you could move the vector anywhere you want. So it'd be the same vector if I moved it over here, as long as it's got the same length and got the same direction. That's all a vector is. Remember, it's like a road sign. A vector's like a road sign. It goes this many miles to Modesto or whatever, right? In this direction. Head this way for this many miles. That's what a vector is. It's got a length and a direction. How many miles and what direction? And you could move that road sign anywhere you want. So those would be the same vector, wouldn't they? They're both the minus. This vector also goes back 7, up 15, doesn't it? So they're both the same. Doesn't matter where the vector sits. I just think it's easy to put them at the origin. Just makes it convenient for us. So anyway, how do we find the magnitude? Magnitude being the length. What do we do to find the magnitude of a vector? Well, you can tell it's just the Pythagorean, right? This is like ABC, right? A squared plus B squared equals C squared. And C is the length, which is what we're looking for, huh? The length of the vector. And so how do you turn C squared into C? Well, you root it. So there we go. C is the root of A squared plus B squared, isn't it? That's how you find the length of a vector. It's just the Pythagorean. So in other words, the length of the vector is just the square root of A squared plus B squared. So it's just going to be the square root of the first number squared plus the second number squared. Make sense? That's how you always find the length of the vector. The square root of one number squared plus this. So you don't have to do all this drawing. You don't have to write all the Pythagorean. I'm just doing all that as background. All you have to do is this. And then work that out. That makes sense? So let's do that. All that other stuff with just extra unnecessary background. So 49, 225, 275, 274. And then you root that, and I guess it's 16.55. Rounded to two places. We all good with that? Remember that? I don't know if we did that or maybe barely did that last Wednesday. All right, next, they want us to find the angle. What's the angle, like the heading of that vector? You know it's between what and what? You know, remember, this is 0 here, right? Remember, this is 0, this is 90, this is 180, 270, right? We know that. So what two angles, you know, and we're talking about this angle. Remember, it's always from 0. There's theta. It's the angle starting from 0 up to there, right? That's the angle theta we're talking. This is from 0 up from 0 degrees, from 0 up to the vector. That's theta. That's the angle of the vector. And so this is another way you can specify a vector. There's basically two ways you can communicate a vector. You can say it's minus 7i plus 15j, meaning it's back 7 up 15. That's one way to communicate a vector. The other way is to say, well, it's 16.55 long, and it heads in whatever this angle is, direction. So there's two ways to communicate a vector. You could just go backing up, you know, I and j, back 7i plus 15j. Or you could go, oh, it's 16.55 long, and the angle it's aiming at is whatever angle. So it's between what two angles is theta? It's between 90 and 180, isn't it? So it's something between 90 and 180, maybe 100, 110, 120, 130. I don't know. Something between 90 and 180. Can you find it? How about I let you try?
Big angle or the little angle?
Well, we need to find the big angle, theta.
Okay.
For sure, yeah. This is theta. Theta is the big angle. Theta is something between 90 and 180. That's why I said that to begin with. Yeah, it's not just this little, but actually finding the little, I think, is about the best way to go. And then subtract from 180. Yeah, that's where I'm going to present the book. The show me an example button, which comes from the book, shows a different way, I think, if I remember right. Anyway, it doesn't matter. You can do whatever you want. Maybe I'll show both, and you can do whatever you want. So here's what I'm going to suggest. I'm going to say, let's just find, let me get some space here. Let's just find the little angle, let me see if I can mark it, right here. If I can find this, call this, I always want to use theta, I don't know what to call it. Let's find this angle here. Call this A or something. Yeah, alpha, right. Call it angle A or whatever you want. So if I can find that angle, then 180 minus that will be the other one. Does that make sense? So let's first find it, and then I'll explain the 180 thing if that's not making sense for you. So let's find that A. How do we find that? Well, there's probably a lot of ways you could do it. Maybe it was I don't know. I think the easiest, though, would be, remember that this is back 7i, and this is up 15j. So this is a little triangle, 7 in this direction, 15 in that direction. It's a right triangle, huh? You with me? This would be the easiest way, I think. It goes back 7, up 15, doesn't it? Because the vector was minus 7i plus 15j, huh? So it goes back 7, up 15. So it's a right triangle because, you know, I and j are perpendicular, right angles to each other, right? So it goes back and then straight up. So it's a right angle. It's back 7, up 15. So this angle A, and once you have a right triangle, once you have a 90 degree, are you getting the hang of this? When you have a 90, you can use Sohcahtoa, right? All the unit, circle, trig stuff we've learned, Sohcahtoa, all that, that's in right triangles, right? So I'm in a right triangle, so I can use Sohcahtoa now. Sohcahtoa. So what? Well, tangent would be the easiest thing, huh? Tangent of this angle A here is opposite over adjacent. Since I don't know the hypotenuse. Well, I do. It's 16.55, but that's a rounded number. I'd rather not deal with that. So that's why I'm not going to use sine or cosine because they both involve the hypotenuse. I'd rather not use the hypotenuse, a rounded number. So I'm just trying to do the very easiest thing. And so I think this is about the very easiest thing. Tangent is opposite over adjacent, right? So the tangent of this angle here, not the original theta. I'm putting the little, it's the reference angle, isn't it? It's the one from the x-axis, huh? That little reference angle, that little angle in the triangle, the tangent is opposite over adjacent. So the tangent of that angle A is 15 over 7. We don't need to use pluses or minuses. We don't care about that, right? We're just saying tangent is 15 over 7. So tangent of A is 15 over 7. How can I find A there? All together? Tangent inverse, right? We all good? Tangent inverse. Oh, and I, here you go. You. Okay, so make sure you're in degree mode. Check your mode. I'm in degree mode. Tangent inverse, 15/7. I'm getting 64 by 9/8. I don't know how many places they want rounded. Oh, nearest tenth. Oh, so it's going to, 64 by 9/8, yeah, that rounds to 65.0 degrees, doesn't it? Everybody good with that? Rounded to the nearest tenth. So 65 degrees. So that angle is 65 degrees. Careful, though. That's not theta. That's A. Now I got to take away from 180. But first off, before I go and do that, is everybody okay with how I got just that angle, A? Right? Opposite over adjacent. Tangent is opposite over adjacent when you're in a right triangle. So I've got A. Now, does it make sense that you write it this way, that theta, see here's theta, right? Theta is from 0 to the angle. That's always what theta is for a vector. It's from 0. So 0 to the angle. Theta plus A, don't you agree that theta plus A must make 180? Right? This plus this. Together they make a half a circle, don't they? Right? So if you want to solve for theta, move A to the other side. Theta's 180 minus A, isn't it? See that? So you don't have to do all this. You can just say, look, it's 180 back up A, right? It's because this is 180 right here. So it's 180 and then, so if you say 180 back up A, you'll have theta. So then you just take 180 minus A. Let's do that. So 180 minus 65, theta equals, what was that, 115? 115 degrees. That's the heading. So we said it was between 90 and 180, and it is.
So that negative 7 doesn't...
Excuse me.
The negative 7 doesn't do anything?
No. Well, yeah, good question. Yeah, the fact that it's negative there...
Oh, it shouldn't matter because it's a vector.
Yeah, well, see, the deal is I'm really pulling that triangle out of the context of the second quadrant. Because I'm not, the fact that this negative has to do with the fact that the angle's really way over here. I don't know if I'm making any sense. Yeah, don't use that. That'll mess you up. Don't use that as negative because I'm just pulling this triangle, just popping it out of its context and just setting it down like right here and saying, what's this angle here? You know, and so this is just a real life link. So the Sohcahtoa, yeah, maybe I could say it this way. The Sohcahtoa relationships are all for everything positive. Sohcahtoa relationships are for real, let me say it this way. They're for a real life triangle that's where the angles are all less than, well, I'm saying it various ways, not very good. Yeah, Sohcahtoa, all these relationships are in right triangles.
Yeah.
So you can't really have a right triangle in the second quadrant because the angle to get there is more than 90. Am I making any sense? Sohcahtoa assumes first quadrant. Right? Why? Because Sohcahtoa assumes a 90-degree angle. And if you have a 90, you can't have another one bigger than 90 because that'd be more than 180. How about that? You guys with me? If you have a 90, he's the biggest. Right? Because 180 total in the triangle. If one of them's 90, you can't have another 90 or bigger. Right? So what does that mean? Well, then Sohcahtoa, which assumes a 90, the 90's the biggest. So what? Well, that means you're in the first quadrant. Because you can't be in the second. Because to get to the second, you have to have an angle bigger than 90. You're not in the second. Sohcahtoa assumes first quadrant. So that means no negatives. Everything's positive in the first quadrant. So whenever you do so, you think, well, yeah, but you're in the second. Yeah, but I'm not really using the angle for the second. Right? The angle for the second is really more than 90. It's the 115. I didn't really use 115. When I said I want A, I used the one that really would be what this triangle would look like in the first quadrant. Am I confusing you by all that? Whenever you do reference angles, let me say it that way and I'll be done trying to stumble around making this clear. Whenever you do a reference angle, you're really back in the first quadrant. You're saying, what would it be if it was in the first quadrant? Because I'm just using this little angle here, which is not really the angle that gets you into the second quadrant. Right? So whenever you do Sohcahtoa or use a reference angle, everything's positive because you're really putting that thing in the first quadrant. That's what you're doing. All right. Good. So we good there? So there's a lot of talking to say. All you got to do to answer these two questions is the square root of a squared plus b squared. That gets you the length of the thing. And then to find the angle, you take the tangent inverse of the y over the x. It'll always be that way. And then figure out what quadrant you're really in.
So does the language of directional angle tell you to find the bigger angle, not the reference angle?
Right, because you know where it really is, because it's back and up, so it's really in the second quadrant. Does that make sense? So yeah. So am I making sense on that, guys? So if they when they give me minus, what was it, 7i plus 15j, I think right away, I know I'm in the second quadrant. I know I'm in the second quadrant, and so there. And then when I do the tangent inverse of y over x, I just make them all positive. I'm casting it into the first quadrant, reference angles. Find my answer of, what was it, 65 degrees. And then I say, yeah, but it's 65 in the second quadrant. So what is it really? What is it meaning from 0? How far to there? That's the deal. All right, let's try another one. Just making sense. So that minus sign in front of those parentheses needs to distribute boom and a boom like that. So 3i minus 7j minus 3i plus 8j. We good there? Minus in front of a parenthesis always distributes like that. And then boom and a boom. So minus 7j plus 8j. What is that? 1j. All right, that thing really simplifies. So I haven't done any magnitude stuff yet. All I've done is add and subtract the i's and the j's, right? We good so far? So that's really what vector v is. It's just 1j. We good? To there? Now, let's find the magnitude of vector v. Well, how do you find the magnitude? Well, it's the square root of the I squared plus the j squared. Now, what's the I? Well, it's 0. There's no I at all. So it's 0 squared plus 1 squared. Guess what that's going to be? Square root of 1 squared, square root of 1, 1. Yeah, so that was kind of a silly question. We get, obviously, the length of a vector. What's 1j? I mean, what is that thing? It's 1 straight up, right? Because j is up and down. It's 1 up. So how long is it? Well, it's 1. Right? It's kind of a silly question. Good? You good with that? I'll move on. Okay. I like physics. I think physics is a very good application of math. Physics is like math with all word problems. That's challenging. Physics was the hardest thing I did in junior college. Yeah.
So they wanted the directional angle on that last part.
Oh, did they? Did they? I didn't notice that. Oh, yeah. Let's go back and do that. Thank you. Thank you. All right. So, yeah. What would the direction angle be? Yeah, here's the vector. Here's the vector right here. It's straight up, right? 1j, straight up, right? I is sideways, j is up and down. Yeah, so what's the angle? Always starting from 0. So the angle, whoops, is, let me do the color here. So the angle is this angle here, theta. What is that angle?
90.
90. I'm not going to do any tangent stuff. It's obviously 90. Done. Is that okay? Just draw it, it's obvious. I'm not going to do any. I mean, you could do the tangent stuff if you want to. What would be the rule? Tangent of the angle A is y value. Remember, it's the y value over the x value, right? Opposite over adjacent. What's the y value? 1 over 0, because there's no x value. I mean, it's 0. X value is 0. 1 over 0. Tangent of A is 1 over 0. How are you going to do that in your calculator? Guys with me? Tangent of A is 1 over 0. Tangent of A is 1 over 0. Guys got your calculators? Can you make that happen? No. You go 1 over 0, it's going to say air. It's not going to let you go on from there and hit tangent inverse. This is where those people in pre-calculus and calculus that just hit the buttons on their calculator all the way through trigonometry and never understood anything that was really going on. They just pushed the buttons, sine, tangent, inverse tangent, cosine. Just hit them buttons and there was nothing happening up here about what was really going on. And they come into calculus. I've taught them in calculus a lot of times. And they'll go, Mr. Herron, my calculator's saying error. I don't know what's going on. Now I'm always thinking in my mind, what happened in your trig class? What happened? You should know that. So what you tell me, so the calculator can't help us here, but you guys know, huh? What angle has a tangent? Remember what tangent is? Tangent is y values over x values, right? Sine over cosine. Tangent sine over cosine, and sine is y values, cosine's x values. This is what I expect them to know. This is what you all know, right? Because you know the trig functions. Tangent is sine over cosine, right? And sine is y. Cosine's x. So when they look at that 1 and 0, when we look at that 1 and 0, we should think, oh, y is 1, x is 0. So where on the unit circle is over 0 up 1? Over 0 up 1 is right there. That's over 0 up 1 on the unit circle. So what angle is that? 90 degrees, which you all know quite well, right? So your calculus teacher won't give you that look. Like, what happened in your trig class? You'll say, Mr. Heron taught me that. Well, you don't need to say Mr. Heron taught me that, but you'll comfortably know that, right? Good. Yeah, because calculator can't do everything. That's why I'm all taking the calculator away on different tests. I'm really not trying to torture you. I've seen all my years of teaching calculus and seeing students give me a blank look, and I think they survived trig by their calculator, and they didn't really get it. And that harms them when they get to calculus. All right, so there we go, 90 degrees. All right, so quarterback releases the football, speed of 48 feet per second, angle 45 degrees with the horizontal. Turn it into a vector. So now we're going the other way. You guys see the game we're playing? That was a pun. This is football. All right. No, I didn't really mean to do a pun there. So we're playing this game back and forth. A minute ago, they gave me like whatever it was, minus 7i plus 15j. And they said, hey, turn that into like length, magnitude, and angle. Right? And now they're saying, okay, here's length. It's like length. And angle. Turn it back into the ij thing. So we're going back and forth between those two languages to describe a vector. Do you get what I'm saying? There's two ways to describe a vector. Like I could say 1 and uno. I'm saying the same number in two languages, aren't I? I could say, back over here, I could say minus 7i plus 15j. That's this vector. Or I could say 16.55 long at an angle of 115 degrees. Same vector. Two different languages to talk vector, right? We could do it with I and J. We could do it with angle and length. So now they're saying, okay, here's a football one. They're giving me length. That's the same thing as length, even though it's really speed. And angle, whatever, magnitude and angle. Turn it back into IJ, please. That's all they're really saying. We're just going between the two languages. Okay. So how do we do that? Well, it's always helpful to draw these things. Let's draw these things. So the quarterback is throwing the football at 45 degrees. That's the angle. And the magnitude is 48 feet per second. That's the length of the vector. So there's the vector. We good there? There's the football flying out of his hand at 45 degrees at 48. If you want maximum length, if you want something to go as far as you're throwing a rock or a football or a baseball or whatever, and you want it to go as far as possible, you should throw at 45 degrees. That is actually the best angle. If you throw a higher angle than that, then you'll get more height, but not. I'm talking about if you want to get maximum distance before it hits the ground. 45 degrees, but if you go higher than that, you get, it falls too short. If you go lower than that, the gravity pulls it down too quick. So anyway, physics, you calculate all that kind of stuff. I'll just tell you the answer. It's 45. It's right in the middle of 0 and 90. It's not a big surprise, kind of like what we might expect. So it's 45 degrees is the best angle for maximum distance. Anyway, because gravity is always pulling down on objects. Physics gets into all that. Anyway, so what we want to do is turn it into an I and a J. We want to find an I, so that's how far over, how far up. What's I, what's J, make a right triangle. Because I and J are always at 90 degrees to each other, right? Yeah. So you good? My job is to find the I and the J. Change from the angle length talk to the IJ talk. Change languages, same vector, different language. So how do I find those? Call this I and J. How do you find those?
Unit circle length times 48.
Yeah, Sohcahtoa, our old friend Sohcahtoa, right? Various ways you can do this. Start with angle 45. Want to find J? That's opposite over hypotenuse, isn't it? From 45, right? This is the side opposite, and this is the hypotenuse. So the sine of 45 degrees is opposite. It's the J over the hypotenuse of 48. You with me? Not a little right turn. Whenever you have a right triangle, you can do Sohcahtoa. Everybody good there? Is that okay? Right? Sine of 45 is opposite over hypotenuse. The A down here is the adjacent side, right? Remember, the adjacent side is right next to the 45. The opposite is across from the 45, and the 48 is the hypotenuse. So, so now, how do I solve this little equation? Sine 45 is J over 48. How do I solve that for J?
Times 48.
Times 48. Exactly. Come on down. 48. 48. Zippo. J equals 48. Sine 45. What do they want? An exact answer? What do they want? Oh, exact answer. So they don't want me to just get a decimal. I was reaching for the calculator. They don't want a decimal thing on the calculator. They want radicals, square roots, and stuff like that. Exact answer. No rounded decimals that are just approximations. So how do we do that? What's the sine of 45 without using our calculator? Yeah, do you know that? On the test, you'll have the unit circle again, on your thing. So where is that unit circle? Okay, so what are we looking for? We're saying the sine of 45 degrees right here. Remember, cosine is x, sine is y, sine is root 2 over 2. Right, so root 2 over 2, so we get, coming on down here, we have got 48 times root 2 over 2, sine of 45. Everybody good there? So how do you deal with 48 times root 2 over 2? What do you do when a whole number interacts with a fraction? Put it over 1. Cross cancel 2 into 48. 24 times, so it's 24 root 2. That's our J component. We've got to find the I now. 24 root 2 is the J component. Good to there so far. I think the I is going to be the same, isn't it? So let's find, how do we find the I? Go back to our triangle, and 45 degree angle, I is adjacent over hypotenuse. So adjacent over hypotenuse, that's cosine, huh? So cosine of 45 is adjacent I over hypotenuse 48. Good, same thing, solve for I. Multiply both sides by the 48. If I can squeeze it in here. Cancels. So I is 48 cos 45. Go to the unit circle. Cosine 45 is the same as sine 45. Root 2 over 2. So it's 48, root 2 over 2. Same thing, 2 goes into 48 over 1, 24 times. 24 root 2 is I. So the vector is 24 root 2I plus 24 root 2J. There's the football vector that's the same as 48 at 45 degrees. Does that make sense? Very useful in physics. Go on to physics to do all that kind of stuff.
Do you think they got a math job in football?
What's that?
Do you think each football team has their own math?
That's right. They got to know that math. Throw those footballs now. All right.
I got a question.
Yeah, Chinu.
They just showed this formula that V equals magnitude cosine theta I. But
Yes.
yeah.
Excellent. Let me just write that down for you, because that's nice and convenient. Yeah, because I'm working it all out, but that's a good way to go. I do like that. So let me write that down. Thank you, Chinu.
No, but when you worked it, I understood why that was the formula.
Yeah, no, but it's good to, sometimes it's good just to have nice, quick formulas, and this is one of those times. Yeah, and I was meaning to that, and I would have forgot if you didn't remind me. Yeah, this is a good time because I like to give canned formulas when it's reliable and it'll always work, and this always will. So Shanu's right. Let me give you the formula. So you don't have to do all that triangle work. It'll always come down to this: magnitude of V, which is the length, right? That was the that was the 48. cosine theta I plus magnitude of V sine theta j. It'll always work that way automatically. So from now on, we won't need to draw the whole triangles and do all the stuff. Whenever they give us a vector and they go 48's the length, the angle's 45 or whatever angle they give, this will always work for any angle, even when it's bigger than 90. So it's real nice. I think it's the best way to go. So you just go, oh, okay, the vector is magnitude, which is the 48. Let me just redo it and show you how easy it is. Cosine of the angle, 45i. And magnitude, 48, sine of the angle, which is still 45j. Just like that. You don't have to draw the triangles or anything. Why is that true? Why is that formula always true? Well, because cosine is always x, huh? Remember on the unit circle? Cosine is always the x value. Cosine is always x. Cosine. So x is sideways, huh? So cosine is always with the I. Does that make sense? See how these things all connect up? Cosine is always the x value on the unit circle, so cosine is always going to be the sideways movement, the I component. When you break a vector into sideways movement and vertical movement, which is a lot of what you do in physics, because you're interested in how far that ball travels sideways, how far it travels up and down, all that kind of stuff. And j, sine, is always the y component, right? Up, down. Remember me saying that it's always cosine is x, sine is y, cosine is x, sine is y. So it makes sense that sine goes with j, up, down. And then you'll just jump right to it. 24 root 2i, 24 root 2j. So we'll just always do that from now on. That's always reliable.
Yeah.
So you don't have to draw the triangles.
Because sometimes you'll get an angle that isn't easy.
Yeah, if you get an angle even bigger than 90, this handles it. This handles the negative thing for you. When it needs to be negative, it makes it negative. Automatic, everything's great because of the sines and cosine. Cosine is always x. It handles it. It's nice. All right, good. So vector is described. Change it to ij. So 146, that's the magnitude. The angle is 5 degrees. Give it a try. So change it to ij. So use the formula I just gave you. V is magnitude times cos theta, I, plus magnitude times sine theta j. No need to draw triangles. That's the result of the triangles. And they want, and this time, 5 degrees is not one of those we have on the unit circle, huh? It's not one of our memorized values. And so that means just use your calculator. And also, see, they say round to the nearest tenth. That also means you're just going to use your calculator, right? So we're just going to go 146 cosine of 5 degrees I, 146 sine of 5 degrees j. Good? Make sense? Hit the buttons on your calculator. Make sure you're in degree mode. This is a 5. My 5s look a little funny. Tenth. So 145.4 I. And 12.7 J. Guys getting that? There is the vector. Easy enough to convert. So just put that little formula on your 3x5 card for the test next Wednesday. Meaning this formula right here. And that's how you will convert from magnitude and angle to I and J. Questions on that one? And of course you need the unit circle. Let's see, okay. Length of the shadow. The length of the shadow for V in the figure shown is the absolute value of the vector's horizontal component. The magnitude and direction angle of V are given. Okay. Write V in terms of I and J, then find the length of the shadow. Write V in terms of I and J, then find the length of the shadow. Okay. So, it's a little weird. So let's do that. So let's find the IJ thing again. You know the formula. It is magnitude of V cos theta I plus magnitude of V sine theta j. So same formula at first. We'll just do that. So that's going to be 1.7 cosine of 25 degrees I plus 1.7 sine of 25 degrees J. Let's get those numbers. And I'm getting round near tenths. So I got 1.54. So 1.5 I plus 1.7 times sine of 25. 0.718. So 0.7 J. Y'all getting that first off? That good? That's the first question. Find the vector V. The second question is find the length. Am I racing ahead of you? You guys caught up? We okay? Find the length of this shadow right here. See that shadow? See what they mean in the picture? Can you see that? The vector's up here, kind of diagonally coming down, and then it makes a shadow on a flat horizontal surface. How long is that shadow? Well, do you see that it's just the x component of the vector? What do I mean? The vector goes over and down, doesn't it? It's got an I component and a j component. Do you see that this I here is the length of the shadow there? They're the same thing. That's all the shadow is the over component. The shadow does nothing with the up-down, right? Right? If I do my shadow of my hand above this table, it doesn't matter how high or low I am. It doesn't affect it, right? It's just the width of the horizontal component is all that matters, the shadow. So straight down, it's just the horizontal. So they're just saying it's just the icon, it's just this. So the shadow is just the 1.5. Feet, inches, miles, what are we talking about here? Inches. 1.5 inches. Is that good? And that's what they said up there. It's just the vector's horizontal component. Now, I don't know. Now, do they want us to say the j is negative because it's going down? That's the only thing I'm not clear on. I don't know. Let's go type in the answer. So is that one okay then? Anything more? So it's just those were the right answers.
We're working with distance, so we got all the positive.
Sure. Yeah. Yeah, it's all just perspective. So, all right. Let's go on to number 20. Magnitude and direction of two forces acting on an object are 120 pounds at south 73 degrees east and 100 pounds at north 57 degrees east, respectively. Find the magnitude to the nearest hundredth of a pound and the direction angle to the nearest tenth of a degree of the resultant force. Welcome to engineering. This is basically the very beginnings of engineering. So, what are they talking about? Well, suppose you have a box or whatever, okay, and you've got two forces acting on that box. What's the result of those two forces? So one of the forces is acting with a force of 120 pounds, right? Pounds is English units for force. So 120 pounds of force at an angle south 73 degrees east. Now, are you good with those direction things? Those are just going to keep coming up and up and up and up. You want to be comfortable with those angles. You want to be able just to whip those out without even a hesitation. So when they say south 73 degrees east, can you find that? Let me give you a second. Find that in your own paper. See how good you are with that, and I'll review it with you too because it's important. But let me give you just a second so you know where you're at, how much you need to pay attention to what I say or how much you already get. So try that. South 73 degrees east. So draw that real quick. You don't have to put it on the box, just draw it in a coordinate system. Whereas south 73 degrees east. So remember what you do. Whatever comes first, that's where you start. So south. There's straight south, right? south, and then from there you go 73 degrees towards the east. This is east. This is west, right? This is north, right? So south, but then you bend 73 degrees, which is most of the way to 90, 73 degrees to the east. So the actual vector is right there. That is south, 73 degrees east. Everybody good with that? You comfortable with that kind of thing? So they're saying, hey, we got this box and something's pushing on it with 120 pounds, lbs, right, per pounds, at south 73 degrees east. So maybe some kind of crane or a person is pushing down and right on that box at an angle of south 73 degrees east, 120 pounds of force. And then somebody else is pushing on that box with 100 pounds of force at north 57 degrees east. What's that? Can you find that one real quick? So find north 57 degrees east. So north, that's straight up. You always start with whatever comes first, right? North is straight up. But it's from there 57 degrees east of that. So again, east is to the right. So from north, little more than half, 57 degrees east of north. Right there. North, 57 degrees east. Is that good? You guys getting the hang of that? So whatever comes first, like south, you do that first, and then 73 degrees towards the east. Or north, do that first, 57 degrees to the east from that north. So it's from whatever you started, from north, or if you started with south, from south. Is that good? Now, and so that's the other, so there's another force acting on this box of 100 pounds, a force of 100 pounds, at north 57 degrees east. So we got two forces acting on that box, or well, I just made up a box, whatever it is, or some kind of object being pushed on by two forces in two directions. What's going to happen? What's the result? I mean, one of them's pushing down and to the right with 120 pounds. The other's pushing up and to the right, or pulling up, somehow forcing up and to the right at 100 pounds. In the direction north 57 east, the other one's south 73 east. Certainly it's going to go right. Both the forces are going east, right? There's certainly an easterly force. But is there an up or a down? Is that box going to move up or down? One of the forces is down, the other's up. Force is stronger down. But is the angle more down than the other angle? Right, you could push down harder at not very steep down angle, and somebody else push up lighter, but straight up, and there's more upward force actually in that. You know what I mean? You guys understand that? This 120 pounds is more than 100, yeah, but not all 120 pounds is going down. A lot of it's going to the right. How much of it's actually going down? I don't know. We got to figure that out. And then this, over here, this 100 pounds is up and to the right, but how much is to the right and how much is up? It's not all right, it's not all up. That's what we got to figure out. That's physics, that's engineering. We got to figure out what's going to happen to this box. This is how they calculate all this kind of stuff. This is how they figure out what's going on when they build bridges and they set up pulleys and they make things. This is how engineers calculate the forces on an object and whether something's stable or not and how much it can withstand and where it's being moved. It's all these calculations. Okay, so what do? Basically, we change both these vectors into ij, add them up, get a resultant ij. That makes sense? That's the game plan. So we take this south 73 degrees, 120 pound thing, and we say, we need I and j, please. We need right and up, down. We need to break it into the sideways force component and the up-down force component. Then we take this one, we say U2, please. U north, 57 degrees east, 100 pounds. We need to know how much sideways force is that? How much I? How much J is that? How much up and down? And then we have the two I's. We add them up because they're both going to be to the right. And then we take one of the J's is going to be negative. This J is going to be negative, clearly, downward, right? And this J is going to be positive, clearly. And then we'll find out what the result is. Is it, in the end, is it more up or more down? And then you'll know if that box is going to move up or down. And we know it's going to move right. And how much force is going to be going to the right in the end? How much force is up or down when all is said and done, when the two forces balance? How much will they balance? How much is left over? So we got to make them both into IJ. All right. So let's do that. So let me go. Well, let me just do it right here. How do we do that? Well, to do that, remember what we just learned. You know the formula, right? Cosine theta I, sine theta J. But first, you need to get the actual angle. Now, what do I mean by actual angle? Do we have the actual angle? I mean, this is 0 degrees. How much to there? That's theta. I need the actual heading of the angle to plug into the cosine theta I, sine theta J formula. I need to know this vector here is at what angle from 0? From 0. So from, bless you, from 0 all the way to here. What angle is that? Well, it's 270 to here, and this is 73 more. So theta is 270 plus 73. What's that? 343? 343. That's the actual angle. 343 degrees. Everybody with me so far? Everybody see what I did? You've always, now we'll just plug that into the, we'll just take the 120 cosine theta I plus 120 sine theta J. And we'll make it into an IJ vector. But you got to get the actual angle from 0. When I say actual angle, I mean from 0. Like we're used to. 0, 90, 180, 270, that kind of thing. So I just did 270 plus 73 because I knew it was south, 73 east. So 73 past 270. Right? Can you do the other one? Find the other angle. What is that actual angle there? Give you a second to try that. I don't know if you can read my writing. This is 57 here. Let me make that a little nicer. There. So find the actual angle of this one. That means from 0. Actual angle means from 0. So this is 0 here. So this is the angle theta right there. From 0 to the angle. Right? It's that. Just like this one was from 0 to the angle. Right? So he's from 0. So what is that? How do we figure out from 0 to that angle?
90 minus 57.
90 take away 57, right? Because it's here's 90 straight up, but it's back 57 from 90, isn't it? Does everybody see that? So it's the angle theta is 90 minus 57, which is 33 degrees. So that angle is actually 33. The other is 343. Is that good? Now we have those two angles. We have the lengths. This one's 100. This one's 120. We go to the formula. So let me get a fresh screen here. So we say, all right, so the first one, the 120 pounds is at, what is it, 343. 343 degrees. So we go, okay, so that's 120 cosine 343I plus 120 sine 343J. That formula we just learned, right? How to turn angle and magnitude into, well, I didn't call it V. How to turn angle and magnitude into IJ. Right? It's just whatever the length is, the 120, times the cosine of the angle I, because cosine is always sideways, so it's I, sine of the angle J. Good. Hit the buttons on your calculator. The final answer, they want rounded to the nearest hundredth, 2 places. 100 has 2 zeros, right? 2 places. But you know what, guys? I'm still in the middle of the problem. I have more where this isn't the end yet. So we better use let's go 4 places for now. Let's use a couple more until you get to the end so that you don't throw things up. So whenever you're in the middle, use a couple more. So cosine 343. So I'm getting 114.756 The other one I'm getting, negative. See, it automatically goes negative, which we know it's down. That other one's down, so that's why this works beautifully. 35.0846J. We made that first force. Remember, that's the one that goes here, down and to the right. See how it is down and to the right? So it's positive I, negative J. That makes sense, huh? So we know 114 pounds is to the right. That's only 35 pounds downward force. See how that works? So that 120 pounds breaks in, at that angle, breaks into 114 sideways and 35 pounds downward. You might wonder, hey, they don't add up to 120. No. It's not a linear thing where they just add up to be 120. There's angles in there. There's directions. There's parts of it here and there, right? So 114 sideways force, 35. So that means that it's the same as if you push sideways on that box with 114 pounds and straight down on that box with 35 pounds. You set a 35-pound weight on the top of that box, pushing down. That's the effect. And sideways force of 15 pounds. Makes sense? Let's do the other one. The second vector, which was 33 degrees, 100 pounds. So it's 100 at 33 degrees. Same formula. It's 100 cosine 33I plus 100 sine 33J. Same formula. Let's figure that out. I'm getting, let's use 4 places for now. 83.8671I plus sine 33 54.4639 J. Good there? So there's that other force, right? That's that one that's going up and, whoops, I'm erasing it, up and to the right at 100 pounds. That ends up having a sideways to the right push of 83 and an upward push of 54. So that one's actually got a stronger upward force, doesn't it? Even though it was lower pounds, more of it was in the upward direction because it was more upward than the other one was downward aimed. So now we just add these two. We just add them up. Once you got I and J, it's nice. Just take this plus this and add up the two forces. You want the result? Add them up. That's what's so great about I and J. Once you get into the I and J, everything's easy. Just add them up. So this I plus that I, just use your calculator, 114.7566 plus 83.8671. I'm getting 198.6237I. And then the other two, so the negative 35.0846 plus 54.4639 is positive 19.3793J. There is what we call the resultant force. There's the result of those two pushes. Together, they'll have that effect. Almost 200 pounds of force to the right and about 19 pounds upward, actually. That box is going to move up. And now what's their actual question? Find the magnitude. The magnitude. So how do we find the result? They want the result. Find the magnitude and direction angle of the resultant force. So now they want me to turn this final IJ resultant answer back into magnitude and angle. So we can do that. Okay, so how do you find the magnitude of that thing? Well, square root of a squared plus b squared, right? Remember that? So I'm going to go, you guys got that copy down? I'll go to a fresh screen and we'll do magnitude. So we are still on the same problem. So the resultant, 198.6237 plus, what was it? 19.3793 J, and so the magnitude, like how much force is it? Because that's the sideways and the vertical, but really, how much force is it? What's the magnitude? So it's the square root of the 198.6237 squared plus 19.3793 squared. So use your calculator. Here you can round to just two places. This will be our answer. So we don't need to worry about more places now. And I'm getting 199.57 it rounds to pounds. So it's just about 200 pounds. So the result of those two pushes is just about 200 pounds of force. Now in what direction? So let me go back, type that in, make sure it's right. 199. Get the angle. So they want the angle also. So how do we always get the angle? The inverse tangent. Y'all with me? But you got to remember what quadrant it's in. Yeah, I don't know if I made sense out of that. Let me say that more clearly than I have. To find theta from IJ, to find theta, you do inverse tangent of the j component over the I component. Because tangent is always y over x, right? So that's j over I. J is up, down, I is sideways. So you always do the inverse tangent of j over I, but then change to correct quadrant, because that assumes first quadrant. Oh yeah. I'm not being very clear. Do the inverse tangent, make it positive for both. Yeah, make it positive for both. Just make both those guys positive, I and j. Do the inverse, and of course this one they already are. This one they're both positive, so it's just going to work real nice and easy. That one is first quadrant, right? This result, I'm erasing it. This resultant vector is in the first quadrant, isn't it? It's right and up. The resultant vector is kind of like that. It's over 198.6237, and it's up 19.3793. So the resultant vector is right and up, isn't it? It is a first quadrant vector. Y'all with me? You see that? So the angle theta, which is right there, will be opposite over hypotenuse. No, opposite over adjacent. So you see how it's the j over the I? It's always the j over the I, isn't it? But if it's in second, third, or fourth quadrant, you're going to need to adjust things. So that's why I say you make them both positive. In other words, you just put it in the first quadrant. Get your angle, and if it is in the first quadrant, you're done. If not, then you need to change for whatever quadrant. All right, so let's do that. So inverse tangent of the 19.3793 over 198.6237. Hit the buttons on your calculator. I'm getting the angle 5.57 degrees. Y'all getting that? 5.57 degrees. That's the angle of this vector. Which is, looks like a small angle on my picture, and that's right. It's a small little 5.5 degree angle. So the result of those two forces, let's go type the answers in. Oops, that's not where the answers are. Go down. All right, well, anyway, back to here. So there we go. Does that make sense on that problem? Let me talk it out for a minute if I can use this time to be helpful while Math Excel thinks it over. So everybody gets it. So let's go back to the beginning there. What did we do on this problem? They gave us these two vectors. First off, this was a lot of work, wasn't it? We had to draw them first off. South, 73 degrees east. We had to draw it. We had to go south and 73 east. And then find out that that was 343 degrees. And north, 57 east. Had to draw it and find out that that was 33 degrees. So get the two angles. And then we had to change them with 120 cosine, 120 sine for I and j. 100 cosine, 100 sine for I and j for the other. Get both ij vectors here, and then add them together. Add and subtract the I with the I and the j with the j. Get the resultant vector, and then we had to go back into the theta thing. So then we took our resultant, and we said, okay, now, put this back here, it looks kind of funny. Now we had to take that vector and go, okay, magnitude squared of a squared plus b squared, 199.57, and probably the part that might be the most confusing for you is finding the angle. So let me go over that one more time. How do you find the angle? Well, I would really suggest you draw it first, right? And I just mean to find out which quadrant. I don't mean real exact or precise. You can tell my drawings are very sloppy. All that matters is the quadrant. Which quadrant are you in? Right and up. Right and up. I'm in the first quadrant. So if you're in the first quadrant, it's just inverse tangent of j over I, because the j is always the y, and the I is always the x, opposite over adjacent, huh? Remember, tangent is y over x, sine over cosine. So j over I. Inverse tangent of j over I, you got your angle. Now, if you're in another quadrant, what if I drew it and it was negative here? Let's say the resultant vector was right and down. What if that was a negative j? It was a vector going right and down, so it was in the fourth quadrant. How would I do that? Well, I would still do positive for both those when I do inverse tangent. And I'd get, why? Because I want to get it in the first quadrant first, and then move it to whatever quadrant it's really in after that. So by making both these positive, even if this one was negative at first, make them both positive for your inverse tangent calculation. You'll get your angle in the first quadrant, and then you go, okay, it's 5.57 if it was in the first quadrant, but really, it's in the fourth. It's down 5.57. So what angle is that really? Yeah, you need to go, it's 360, take away 5.57, whatever that is, right? You see how you would calculate it for whatever quadrant you're truly in. Does that make sense? So just do inverse tangent of the positive j over I. Get your answer. Know that's a first quadrant answer. If you're really in the first quadrant, great, you're done. If you're in second, third, or fourth, you need to adjust that. Because that's a reference angle. Remember, whenever we do that, that's a reference angle, meaning that's from the x-axis. That's what it means to be a reference angle, right? Because this all started with 0 on the positive x-axis. So that will get you a reference angle. You just find that angle in whichever quadrant you're truly in. Questions on that? Anything I can answer on that? Yeah, they do if you click the help button, notice they do a sine cosine kind of method. You can do that. I don't think that's easier than the tangent thing. So, for the angle. So, they do a different method. Anyway, all right, here we go. So, same kind of thing. So, we got you don't need to even worry about all the words, whatever, blah, 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 blah. 1650 at north. I'll just write the key facts for you. 1650 at north, 40 degrees west, and 1230, the other angle over here, the other force is 1230 kilograms of force. So this is using metric units instead of English units. South, 50 degrees west. So do all the same stuff. So first off, draw those angles and find the actual angles theta from 0 degrees. Bless you. So north, 40 degrees west. So right there, huh? We good on that? North, but then 40 to the west. So find out what angle theta from 0. What angle theta? Oh, didn't go all the way there. What angle theta is that from 0? So figure that out, and then do the other one. So get both the actual angles, and then you can use the IJ formula to turn them into IJ vectors. So it's 90 plus 40, huh? 130 degrees. We good? So that one's 130. It's a true angle. Everybody see how I found that? So it's north, 40 degrees west. So what is that from 0? That's 90 and 40 more. 130. The true angle is 130. Is that okay? Questions I can answer on that? Everybody see how I'm coming up with that 130? Right? Because that's from 0. It's 90 straight up, and then 40 more. So 90 plus 40, 130. Okay, so now try to find the other one. Draw that one and find that one. So south, 50 degrees west of south. West is to the left, huh? So 50 degrees west, so that'd be like this. So there it is, south, 50 degrees west. So it's 50 degrees west of south. So our job, though, is always to figure out what angle is that from 0. From 0 to that, what angle is that, right? That's what we're trying to figure out. You guys with me? So I drew the south, 50 degrees west. And then, so, okay, what is that from 0? So this is 180 to here. Or you could go to here if you want 270 back up 50, huh? Is that easier? You could either go 180 add 40, or you could go 270 subtract 50. See how those are both the same? Not confusing you? giving you two options. You could say it's 180 and then like 40 more, huh? Because this is 50 and 40 make the 90 here. Right? So you can say it's 180 and 40 more. Or you can say, look, I'm just going to go to 270, back up 50. So it's 270, back up 50. So either way, you'll get the answer 220. 180 plus 40 would also be 220, right? Same spot. That's a 220-degree angle. That's the true angle from 0. 220. So that's what south 50 degrees west is. It's a heading of 220 degrees. Is that good? So now we've got our two angles. So now we can turn those vectors into ij, and then add them up. So do the same thing. Use 4 decimal places to do the next part. So this will be, was it 1650 cosine of 130 I plus 1650 sine 130 degrees J. So I'm getting negative 1060.5996 I plus 1263.9733 J. Good to there. And then the other one is going to be $12.30. Nope, cosine, huh? Cosine of 220 I plus 1230 sine 220 J, which is minus 942.2347 I minus, bless you, something 790 point what? 6288 6288 J. Can you read that? 790.6288 J. You guys getting that? We on the same page? Let me write it on a fresh screen. If you guys got that copy down okay? I'll write it over here. So minus 1060.5996 I plus 1263.9733 J and minus 942.2347 I minus, it's tedious, 790.6286 J. Okay, so we got the two vectors, the I and the J, then you add them up, huh? So the resultant vector, this, and this, you add the two i's, which are two negatives, so they're just going to add up. So 10, 60. I'm getting negative 2002.8343i. The j's, I'm getting plus 473.3447 J. Is that good? How are we doing? Now that's the resultant. Now they want the magnitude. So that's the square root of the first one squared plus the second one squared. So let's do that. And I'm getting 2058.01. Did y'all get that? Is that good?
Yeah, I got that.
Okay. Questions I can answer? Did y'all see how this is coming about? No questions? It's all good? Okay, and then finally the angle. Can you find the angle? Now remember, the angle's a little tricky. Remember what you do. To find the angle, you do inverse tangent of the j over the I, because it's, y over x, sine over cosine, right? But make them positive, because you want to do it in the first quadrant, get a reference angle. Remember. So I'll say positive. So do the positive, so we're going to go inverse tangent of the y value, the 473.3447 over the j, over the I, but just use the positive, the 2002.8343, right? And I'm getting 13.3, just round to one place, they said. I remember that lesson now. 13.3 degrees, but that's first quadrant. If this angle's in the first quadrant, great, I'm done.
So should you keep some more numbers then?
No, it's okay, because we're just going to deal with whole numbers at this point. Where's this angle actually? Where is this resultant vector? So draw him. Let me give you just a second. All right, so they're giving me force 1 and force 2. They've already got it in IJ. This is nice. I'm not going to need to do any of that translating between theta and IJ and back and forth. They give me IJ. They just say, hey, resultant. Okay, you mean atom? Yeah, they mean atom. That's all they mean. So take the 5i minus 8j vector and add it to the 3i plus 4j. Find the result. Add them up. They're already in IJ for you. So the resultant vector, 5i and 3i, 8i, minus 8j plus 4j is minus 4j. Done. There's the resultant vector.
I feel like that question should have came before the other two.
Yeah, that kind of leads the other two. Now, there's a part B, which is actually simple, but I want you to first be caught up with me. We good there? Just add them up, get the resultant vector. Now, think with me for a second. That's the result of those two forces, right? Force 1 is doing something, force 2 is doing something. Together, the result of those two forces is what? Let me draw it. You don't have to draw it, but I always like to see stuff. It's over 8 down 4. It's like that, huh? It's over 8 down 4. 8i minus 4j. So the resultant vector is down and to the right, isn't it? So these two forces are doing whatever they're doing, and the result of them is a downward right force, isn't it? That's the result of those two forces. It's the same thing as if those two forces didn't exist and there was just one force down to the right. Same effect on that object, any object. Okay. Now, their second is, what additional force is required for the given forces to be in equilibrium? Statics is an engineering course that covers things in equilibrium. Meaning, like these folders on my table up here. Why aren't they moving? Because they're in equilibrium. There are forces acting on those folders right now. What am I talking about? What forces? Right? If I set the calculator here, I just let it go. It's not floating. It's not moving. Why? Because the forces acting on a static object, the whole course I took is called statics. I was going to be an engineer until I realized I didn't like it. Once I got to Cal Poly and I changed to math. So I did a little engineering for a while. So I took statics is one of the engineering courses I took. And so that means that an object that's static, that's not moving. They also have kinetic. I didn't get to that. Static, so it's not moving. So it's stopped, which means the forces acting on it are in balance. They're in equilibrium, aren't they? What forces are acting on that calculator right now? Gravity's pulling on everything, right? Gravity's holding us down right now. Gravity is pulling down on that calculator, but not just gravity. Everybody always identifies gravity, and that's true. Gravity is pulling down on that object. But that object is not moving down right now, is it? So there must be something else counteracting gravity with an equal and opposite force, so that otherwise that calculator would be moving. So what other force is acting on that? Gravity's trying right now to pull that thing down. Gravity's trying to pull you down to the ground in that chair you're sitting in. Why aren't you going down to the ground? Because what's the chair doing? It's pushing you up. The chair is pushing up on you with the same force gravity is pulling down on you, and they are in equilibrium. Same thing with this calculator, right? That's why it's not moving. So that table is pushing up on that calculator. Your chair is pushing up on your behind right now, right? Keeping you in that chair. So anything not moving, the forces are in equilibrium. So therefore, this resultant force, they're saying, what if this is the result, down and to the right like that, what other force, right? What additional force is required? Because if you just had an object, say we just had a little ball right here, something like that, and you push down and to the right, that ball is going to go down and to the right, unless an equal and opposite force comes in and pushes back, then the ball won't move. And that's what they're talking about. Equilibrium. Equal and opposite force. So we need an equal. So they're asking, what's the equal and opposite force that needs to push on that ball so it won't go anywhere? Well, here's the resultant force. What's equal and opposite?
Would it be -8 positive?
Yeah, -8 plus 4j. Done. Isn't that easy? So easy. The equal and opposite force. Always reminds me of my buddy that went to Cal Poly with me, my good friend. He's an engineer back in the East Coast. I think he's an executive now. We haven't talked for some years. Anyway, fun guy. He was my friend through high school. And anyway, I remember at junior college, right before we transferred to Poly, junior college, we took some of these engineering kind of classes together, and he actually stayed with engineering. I bailed out. But anyway, and I remember after one of the tests, it was like a statics course. You know, we'd always, right after the test, you know, all of us would be in the hall talking about the test and how it was, and we were like 2 or 3 of us were talking. Yeah, on that box, did you get the box was rotating, but the force here and there, and did you get that one? You know, and then I remember my buddy saying, you know, we're like, yeah, the gravity was pulling down, and then the other person was pushing on it, and the lid was, you know, and we were balancing the forces, and my buddy goes, oh, gravity. I forgot about gravity. And that just cracked me up. He was like, he's real smart, but he would just forget silly little things sometimes. It was just his habit sometimes on tests, you know. And whatever reason, I just don't, I mean, I messed up in different ways, but I'm not careless. That just wasn't my weakness. I did other dumb things, but carelessness, I don't know, whatever reason, I just didn't do that. So I kidded those around me that did, probably mercilessly. I was like, really? You forgot gravity on that box? I said, if there's no gravity, then the upward force of the ground should be making that box rise, right? I said, did you give the altitude at which that box is going to be? You know, I was just giving him a hard time. Because he's like, I never want to talk about the test after this. I hate talking about this. Anyway, it's just funny. So, the forces are in balance there, aren't they? The forces are in balance. All right. All right. So, can you do that? Can you write those forces? Force 2 looks the trickiest. Oh, those units are 2s, aren't they? Notice all the things are 2s. 2, 4, 6, 8. 2, 4, 6, 8. Right? They're all going by 2s. So, for example, like, let's write force 1. Force 1. What's force 1? Negative 5I. Good? Everybody see that? See how force 1 goes back 5. Here's 4, right? 2, 4. It goes halfway. So 5 minus 5I. Everybody good there? What's force 2? Force 2 is the trickiest. Just ask yourself, how far back, how far up? Looks like half a jump back and then 2.5 up. So what is that? So it's back
1 and 3.
1. It's up.
5.
Isn't it 5?
Yeah.
Minus 1I plus 5J. Everybody see that? This is 2, 4, 5. Right there. 2, 4, and then halfway is 5. We good? That's 2, 4, and that's 5. Everybody good? And it's back 1 to this dot here. Good? And then force 3. What's force 3? So go ahead and see if you can find force 3 and force 4. And then when you get them all, just add them up. That's the result. Just add them all up. Add up the I's with the I's and the J's with the J's. And get the resultant force if you can. See if you can get that. Give you just a second on that. So force 3 is what? 5I minus 5J? Am I doing that right? Oh, 6. Is it 6? 6, 6. Yeah, I'm not doing that right. Just said I don't make careless mistakes. There's one. 6, 6, huh? Over 6, down 6. Force, and then force 4 minus 5J. There we go. Is that good? The 4 forces, add them all up. So the resultant, so just add up all the I with the I. So add up all these I components. Was that mine? Oh, it's 0I? Am I doing that right? It looks like 0I to me. And then the J, 5 minus 6 minus 1J. Yeah, I think it's just 0I minus 1J. Did I mess that up?
No, wouldn't it be negative 6?
Yeah, it'd be negative 6. What am I doing? Yep, thanks. So is it right now? It's easy to mess these up. Yeah.
The 2 5s cancel.
Yeah, the 2 5s cancel. Good way to put it. Minus 6J. Is that better now? It's easy to mess up. It might be more helpful to write this would have what helped me from making that small mistake I just made, is to put this, to put the I in there even when it's 0. That way I wouldn't tend to mess up as easily, I think. Anyway, whatever works for you. So there's the resultant force, which is what they're going to ask you for, the resultant vector. And then they're going to say, if that's the result, what's the equal and opposite force that would bring it into equilibrium? So the opposite, to bring it into equilibrium, would be plus 6j. You don't need to do the 0I. That's not even there. Good? Easy? Questions on that one? Figure, small plane, cruising to the right, 177 miles per hour, and bearing north 41 degrees east. They're giving us a nice picture showing that. The wind is blowing from the west to the east at 44 miles per hour. The figure indicates that V represents velocity of the plane in still air, and W represents velocity of the wind. Express V and W in terms of their magnitude and direction angles. Yeah, so basically, what happens if you got a plane in the wind or a boat in the river with a current? Well, both things play onto it, right? The direction of the airplane's heading, the direction the engines are pushing the airplane, and also the direction the wind is going. Both play into the deal, don't they? Kind of running out of time. I didn't realize that. All right. So basically, it's the same kind of thing. You got two vectors. What's the wind vector? That one's easy. That one is to the right, 44. So that's just 44I is the wind vector, huh? So, right, 44. If you want the angle, he's at 0 degrees. So he's cosine of 0 with I and 44 sine 0j. So that one's easy. And then you just got to figure out the V vector, which is the plane's engine, and then they add them together. You add the two vectors together. See how they've added the two vectors? They moved the W one up to here. So V, remember you can move vectors. Vectors aren't anchored anywhere. They're a loose boat. So they took that and they said, let's just move it up here. And so that's vector V plus W. That's how you add two vectors, is end to end, like that. So you say, this vector V takes us from here to here with his arrow, and W takes us straight to the right. So this is the resultant vector. That's how you picture the result of adding two vectors. You add the vectors end to end pictorially, and you can get a picture of the resultant vector, the V plus W resultant vector. So they just have you go through the calculations. It's just going to be like the other one we did. We're out of time, so I'll leave that there.